In these videos, I'm going to be going through math, physics, and engineering practice problems. If you need help with any of your courses, or you want access to extra practice problems, check out my website linked below. In this video, we're going to be taking a look at sound tubes. But before we do that, let's get our equations sorted out. So the first one we're going to need is going to relate the wavelength to the velocity to the frequency. So for sound tubes, we know that the velocity that we're talking about is going to be the speed of sound in air. So we're going to take that to be 343 meters per second. And that's going to be the value for air at a temperature of 20 degrees Celsius. That value does change with temperature, so you'll see on some questions we'll use some different numbers. But if you're not given any information about the temperature of the air, then you can just assume it's 343. For the sound tubes, we need to know whether one end is open or both ends are open, because that's going to change our equations. So if we have one end open, the equation we're going to have for our wavelength is going to be 2L over n minus a half. So n can be any positive integer, so 1, 2, 3, etc. And what that means is that the standing waves that can be formed can be calculated by using different values of n. So the equation for both ends open is almost the same, except instead of n minus a half, we've got n. And same thing, n is going to be any positive integer. If you're looking at other resources, sometimes people do this a little differently, where they use different values for n depending on whether it's one end open or both end open. But for this one, we're just going to use these equations. So I just want to mention that because if you're looking at other resources online, it might be a bit confusing because their equations are a bit different. All right, let's take a look at our first question. We've got a sound tube which is open at one end and closed at the other end. The length of the tube is given as 6 meters, and the speed of sound in air is 344 meters per second. So for part A, they want us to find the fundamental frequency. For part B, they want us to find the second longest possible wavelength. And for part C, they want us to find the fourth smallest possible frequency. So let's start by grabbing our equation. So we know that it's open at one end and closed at the other end. So we're going to have the n minus a half on the bottom of our wavelength equation. For the fundamental frequency, that just means that n is equal to 1. So for the fundamental wavelength, we can calculate that first by saying 2 times 6 meters over 1 minus a half, and that gives us 24 meters for that wavelength. Now we can use that in our other equation to calculate our frequency. So our frequency is going to be the speed of sound divided by that wavelength, and we end up with 14.3 hertz as the fundamental frequency. For the second longest possible wavelength, that's going to be when n is equal to 2. So when n is equal to 1, that's going to be the longest wavelength, and then every n value above that is going to make the wavelength smaller and smaller. So if we plug in n is equal to 2 in our equation, we get 6 times 2 meters over 2 minus a half, and that gives us 8 meters. For the fourth smallest frequency, that's going to be when n is equal to 4, because when n is equal to 1, that's going to be our smallest frequency. So we can start by calculating the wavelength when n is equal to 4, and if we do that, we get 3.429 meters. Then we can go ahead and calculate our frequency with the speed of sound and that wavelength, and we end up with 100.3 hertz. Now let's take a look at another problem where we have a sound tube, but it's open at both ends. And in this case, the length of the tube is 0.8 meters. And for this one, we're going to use the speed of sound to be 341 meters per second. So for part A, they want us to find the longest wavelength that can be produced. For part B, they want us to find the smallest frequency. For C, they want us to find the second smallest possible frequency. And for part D, they want us to find the third longest possible wavelength. So this question will be pretty similar, but we'll just be using a different equation for our wavelength because now our sound tube is open at both ends, whereas in the other one, the sound tube was closed at one end and open at the other end. So let's grab our equation. Wavelength is 2L over n for open at both ends. The longest wavelength is going to be when n is equal to 1. So if we plug in n is 1 and L is 0.8, then we end up with our longest wavelength as 1.6 meters. Now for part B, if we want the smallest frequency, we already know what the wavelength is when n is equal to 1, so now we can just use that with our new speed of sound of 341. Plug in that, and we get 213 hertz. For the second smallest possible frequency, that's going to be when n is equal to 2, so we can first calculate the wavelength when n is equal to 2, and that gives us 0.8 meters. Now we can use that wavelength in our frequency equation with the speed of sound of 341 and the wavelength of 0.8, and that gives us 426 hertz as the second smallest possible frequency. And for the last part, the third longest possible wavelength, that's going to be with n is equal to 3. So if we plug in n is 3 and L is 0.8 meters, we end up with the third longest possible wavelength as 0.533 meters. That's it for this one. If you enjoyed this video, give it a thumbs up and subscribe to this channel. If you have any questions, drop them in the comments below and I'll answer those as soon as I can.